Hello and welcome to this revision session for A-Level Physics Paper 2. So in today's revision session what we're going to be doing is we're going to be looking at how to answer examination questions on AQA A-Level Physics Paper 2. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out, whilst in the right hand side write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. And after the end of the revision session, write up these notes into a revision sheet for you to use independently. So how can you be revising AQA A-Level Physics? So the first step is to learn the key facts. Use the revision guide, class workbooks, prep notes in the textbook to learn the key ideas of the course, and you might wish to write a mind map or write out notes for yourself. The second step is to retrieve your knowledge and understanding. So use Caboodle, Seneca and knowledge checkers. Use cue cards to quickly test your own knowledge. Then finally you should be practicing exam style questions. So using exam prep books, homework books, study books, workbooks to answer exam questions and mark your own work, and this could include downloading past papers from the websites. Now these three steps of learning key facts, then testing yourself, then practicing exam style questions are how you should revise AQA A-Level Physics. So let's now have a look at some questions regarding paper 2 for AQA A-Level Physics. So the first topic we'll look at is gravitational fields. So the first question says, the lines in figure 4 show the shape of the gravitational field around two stars, G and H. Compare, with reference to figure 4, the masses of G and H. Then the next question says, X and Y are 2 points in the field. Annotate figure 4 to show the field direction at X and the field direction at Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, it's important that you know what a gravitational field shows. So you can see that G has the greater mass. How can you see that G has the greater mass? Well, we know that because the field lines coming from G are closer together, and the density of the field lines tells you about the gravitational field strength, which is linked to the mass of the object. The greater the gravitational field strength, the greater the mass of the particles. Now the next question is asking what would you draw for X and Y. So it's important to note that what you would do is you draw tangential arrows at X and Y that flow towards G and H, because a field line in a gravitational field will always go in the direction of a test mass, and because the gravitational force is always attractive, that means the test masses will always be going towards the particles that are shown, so therefore the field lines will be going towards the objects. The next question says, a spherical asteroid P has a mass of 2 × 10⁻20 kilograms and the gravitational field strength at its surface is 0.40 newtons per kilogram. So use this to calculate the radius of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you should understand is you should look on your equation sheet and you can see that the gravitational field strength is equal to big G m over r squared. So you've realised you've got the mass of the object, you've got the gravitational field strength, and you need to work out the radius r. Now what you should do is rearrange the equation to make r the subject, so r is equal to the square root of big G m over small g, pop in the numbers and you work your answer through to be 1.8 × 10⁵ meters. The next question says, sketch on figure 5 the variation of the gravitational field strength G with the distance r. The distance is measured from the centre of P, and then explain what is represented by the area under the graph between r equals big R and r equals 2r in figure 5. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you should understand is as follows, that the gravitational field strength is linked to the distance by the equation G equals big G m over r squared. So because G and m in this instance are constants, we can say G is directly proportional to 1 over r squared. So it's going to follow the inverse square graph. So it should look like so, but what you should also be doing is working out what the values are. So you can see that when the radius is equal to r, well then the value is going to be 0.40. When it's equal to 2r, well again it's G is proportional to 1 over r squared, so therefore it'll go down by a factor of 4 because we've doubled the radius, so then it comes 0.2. You can then do the same for 3r to then show that particular relationship, and making sure that you actually work out the individual values. Now again, what is represented by the area under the graph? Well, it's important to know that the area under the graph represents the work done for an object of 1 kilogram or per unit mass to move from r to 2r. So again, it's very important to know what graphs show in AQA A-level physics, and remember you can work it through by saying that the area under a line is going to be the y-axis value times by the x-axis value, so that tells you it's going to be the work done in this instance. And remember, it's for a test mass because that's what definitions come from, and it's going from r to 2r. The next question says, asteroid P approaches the two stars G and H. Figure 6 shows one position of P close to H. Now the gravitational force on P from G is 6.38 times 10 to the 12 newtons. Now the mass of H is 3 times 10 to the 25 kilograms, and the mass of P is 2 times 10 to the 20 kilograms. The distance HP is 1.5 times 10 to the 11 meters. Calculate the magnitude of the acceleration of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, what we know straight away is we're asked to work out magnitude, and we've been given something like the gravitational force, so how can we link it all together? So what we can say is we can say F equals Gmm over r squared to find the force between P and H, because we can tell straight away that there's going to be the gravitational force between P and H, but also P and G. So you can work it through. So you can work it out by saying F equals Gmm over r squared. Remember, big M is the mass of the larger object, small m is the mass of the smaller object, r is the separation between the two centers of mass. So you can work it out to be 1.8 times 10 to the 13 newtons. Now what we can see is we've got a right angled triangle where we have two sides of the right angled triangle, and we need to work out the resultant. So we can use Pythagoras. And again, it's very important that you can recognize when you've got to use trigonometry in different examples in physics. So we can then say F total square is equal to the square root of the gravitational force between P and H squared plus the gravitational force between P and G squared, and then you work it through to be 1.9 times 10 to the 13. Remember, it's important to note that the gravitational force will be a vector, so you've got to consider what the overall vector is going to be on that particular object. We can then use the equation F equals ma to work out the acceleration. There's always a big alarm bell going off when you've been given a force and asked to work out an acceleration, that you're going to have to use Newton's second law. So acceleration is force over mass. We can pop the numbers in, so it's 1.9 times 10 to the 13 over 2 times 10 to the 20, so we get 9.4 times 10 to the minus 8 meters per second squared. The next question says, the Global Positioning Satellite GPS uses satellites to support navigation on Earth. One GPS satellite is in a circular orbit at a height h above the surface of the Earth. The Earth has a mass of big M and a radius of r, so that the angular speed of the satellite is given by omega is equal to the square root of Gm over r plus h cubed, and then calculate the orbital period of the satellite when h equals 2.02 times 10 to the 7 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, the first thing to note is we're trying to show the angular speed, so how can you work that through? So it's very important that you can relate the gravitational force, okay, which is going to be Gmm over r squared, is going to be equal to ma. That's important because it's shown that it is the resultant force in this situation, but it's also equal to the centripetal force, so therefore equals mv squared over r. So at this point we can then work through our value of omega. Now again, you can work through the values now straight away you actually probably can think that because we need to work out our value in omega, that maybe it's better if we have our centripetal force in terms of omega. So instead of using mv squared over r, we could maybe use mr omega squared and then work our value through. So we can say gmm over r squared is equal to mr omega squared, and then what you can do is cancel through the small m's because they'll be linked together, make omega the subject, so you say omega equals the square root of gm over r cubed. Now r cubed, it works through to be r plus h cubed because actually the radius that you're going to work out, the small r, is the distance from the center of the object to where the center of mass of the object producing the gravitational field to the center of mass of the object that is in orbit. So in this case it's going to be the radius of the planet, big R, plus the circular orbit height, h. So it works through as so. Now in the next question, you're going to have to use this equation. So we're going to have to use this equation of omega equals the square root of big G m over r plus h cubed by popping in all the numbers from the previous question. Remember, we work in meters in our values to get our speed, our angular speed in radians per second to be 1.45 times 10 to the minus 4. We can then look on our equation sheet and see that the time period is 2 pi over the angular speed. So you 2 pi over the value to get 4.3 times 10 to the 4 seconds. Always look on the equation sheet to see how we can link the values together. The next question says figure 3 shows the orbital plane of the satellite inclined at the angle to the equator, and x, y and z are locations on the Earth. X is at the North Pole, y is on a high mountain, and z is on the equator. The satellite is to be launched from one of these locations. State and explain which launch site, X, Y or Z, minimises the amount of fuel required to send the satellite into orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you can either consider it in terms of speeds or energy. So the answer would be Z, because you've got to think about the idea that at that position the satellite has the largest initial speed or the largest kinetic energy from the Earth's rotation, because you should be understanding that at the equator we've got the highest angular speed. So at that point we can then understand that it'll have the most kinetic energy from the Earth's rotation itself, so it'll need the least amount of energy from the fuel it is given to have enough energy to escape the Earth's gravitational field. The next question says, the satellite has a mass of 1,630 kilograms. Calculate the gravitational potential energy of the satellite when in orbit in the previous question. And then a different satellite is in a higher circular orbit. Explain how the linear speed of this satellite compares with the linear speed of the satellite we worked out previously. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's important we understand how we can work out the gravitational potential energy. Now again, because we're looking at orbits, we can't use the equation E equals mg delta H. We've got to use the equation that gravitational potential energy is equal to minus gmm over r. Now we've got big G, it's a constant. We've got the two masses because we've got the satellite mass and we've got the mass of the Earth, so we can pop those into the equation. We then divide it by the separation between the centre of the Earth and the satellite, so we can work it through to be minus 2.44 times 10 to the 10 joules. Now again, remember, gravitational potential energy is always given as a negative value because the gravitational force is attractive, and we set infinity to equal 0 gravitational potential energy. Now the next thing is we can see how the linear speed of the satellite compares with the previous one. Now we've just looked at the idea of how we can work out angular speed, but how can we work out the orbital speed? Well, we can work out the orbital speed by equating the values are the gravitational force equation, F equals g mm over r squared to equal mv squared over r, and then make v the subject. So with that we can work out our orbital speed to be v equals the square root of gm over r. Again, you always should understand how to work out the escape velocity from equating energies and work out the orbital velocity from equating forces. So therefore v is directly proportional to 1 over the square root of r. So by that logic, you can see, in fact, that the higher orbit will have the smaller linear speed from that justification. Let's have a look at some questions on electrical fields. So the first question says, an isolated solid conducting sphere is initially uncharged. Electrons are then transferred to the sphere. State and explain the location of the excess electrons. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you can tell that the electrons are going to be located on the outer surface of the conducting sphere, and that the electrons will be equally spaced on this sphere. Why is that? Because the electrons will mutually repel each other because they're all negatively charged, so they'll want to spread away from each other as much as possible due to that electrostatic repulsion, so they'll be equally spaced out on the surface. The next question says, figure 3 shows how the electrical potential V varies with distance r from the centre of the sphere. The radius of the sphere is 0.10 meters. So the magnitude of the electrical field strength E is related to V by the equation E equals delta V over delta R. So determine, using this relationship, the magnitude of the electrical field strength at a distance 0.30 meters from the centre of the sphere, and state an appropriate SI unit for your answer. Then the sphere acts as a capacitor because it stores charge at an electrical potential. Show that the capacitance of the sphere is approximately 1 times 10 to the minus 11 farads. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's important to note that you've got to work out the gradient by saying, well, obviously E is linked to V by E is delta V over delta R, so from the graph that's going to be the gradient. Now it's going to be the value at 0.30 meters, so because it's curving you will have to draw a line as a tangent which only hits the curve at 0.30 meters. You've then got to explicitly show how you work out the gradient of the tangent by literally drawing in your gradient triangle, and it's got to cover at least 50% of the line drawn from your tangent. You then work out the value through and you get an answer of approximately 2 times 10 to the 6. Now what's the units going to be? Well, if you think logically about this, it's going to be V, okay, over M, because we're doing the potential over the distance, so it's going to be 1 unit over the other unit, which is volts per meter. Or you could also remember the units for electrical field strength from the definition. It's the force per unit charge, so it's newtons per coulomb. Now in this next question, what do you do? Well, you can work out what the value of V is. The value V, it can work out your value of charge by saying V equals Q over 4 pi epsilon 0 R. So you can then look on your graph and work out what the charge will be by saying Q equals V times by 4 pi epsilon 0 R, and then you can work out that value. Now you've also got the electrical field strength at 0.30 meters, so you've got your electrical field strength there. Now because it's a capacitor, we can say that the capacitance is equal to the charge over the potential difference. So therefore we've just worked out the charge in the previous time to be 2 times 10 to the minus 5 divided by your potential difference, which you can then work out to be 1.8 times 10 to the 6. So we get our capacitance of 1.1 times 10 to the minus 11 farads. Or you could also work the other way and say that, well, C equals Q over V. We can work out V by doing V equals Q over 4 pi epsilon 0 R. So therefore C is going to equal 4 pi epsilon 0 R times by V, and work it through to be again 1.1 times 10 to the minus 11 farads. The next question says, electrons leak away from the sphere with time and the amount of energy stored by the sphere decreases. At one instance, the magnitude of the electrical potential of the sphere has fallen to 1 times 10 to the 6 volts. Calculate for this instance the change in the energy stored by the sphere. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? So, you'll note that E is equal to a half CV squared. Now, how do you know that? Well, that's given to you on the equation sheet. How do you know to use that value? Well, you think you've just worked out C, you've got V in the question, so it allows you to easily work out your value. So you can work out what the energy stored is going to be at 1 times 10 to the 6 volts. So then what we can do is then work out the energy stored when it's fully charged. Again, you can see on the graph when it's going to be fully charged. So at that point, you can work out that value there. You find the difference between the two, so it's 18 minus 5.5 to get 12.5 joules. Let's now have a look at some questions regarding capacitance. So the first question says, a capacitance of capacitance 63 picofarads is made from 2 parallel metal plates separated by an air gap. The capacitor is charged so that it stores a charge of 7.6 times 10 to the minus 10 coulombs. It is then isolated. A sheet of mica of dielectric constant 6 is inserted between the plates so that it completely fills the space between them. The mica does not discharge the capacitor and does not change the separation of the plates. Firstly, explain explain what is meant by a dielectric constant of 6. Secondly, mica is made up of polar molecules. As the mica is inserted, the capacitance of the capacitor changes. Explain how the polar molecules cause this change in capacitance. So pause the video now, then unpause the video when you want to go through your answer. Right, well, this first question is asking you to fundamentally define what we mean by dielectric constant. So the definition of dielectric constant is it's the permittivity, which is the ability to make an electrical field, of the medium divided by the permittivity of free space. So what we are saying by that is that the permittivity of the medium, the actual dielectric, is 6 times the permittivity of free space. It can find it easy to generate electrical fields by 6 times the magnitude compared to what free space can. The next question is asked us to understand how polar molecules can change the capacitance. So it's important to note that polar molecules align anti-parallel with the electrical field. So that means the positive side of the polar molecules aligns with the negative plate and vice versa. So because they're all lined up, that will produce a very coherent electrical field from the polar molecules. But because they are aligned in the opposite direction, anti-parallel to the actual uniform electrical field, it will produce an electrical field in the opposite direction, so it counters the electrical field between the uniform plates and reduces the field between the plates. So as a result, the potential difference has now been reduced, but the charge remains the same. So because C equals Q over V, well, that tells us that the capacitance has increased, that the capacitor finds it easier to store more charge between the plates. The next question says, a capacitance of capacitance 63 picofarads is then made between the two parallel plates separated by the air gap. Now calculate the difference between the initial energy stored by the capacitor and the energy stored when the mica has been fully inserted. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this one? Well, we know in this question that the charges remain the same. So we know Q is the same, but the new capacitance is 6 times out of the previous one because the dielectric constant is now times by 6. So when we look at the equation, for example, you can look at your dielectric constant equation by saying, C equals A over epsilon 0 epsilon r d squared. So what you can say by that is the new capacitance is going to be 6 times the size of the previous ones. So you can work it through by saying if Q remains the same but capacitance goes up by a factor of 6, well, then our energy difference is going to be 3.8 times 10 to the minus 9 joules. The next question says, figure 1 shows the structure of a variable capacitor used for measuring angular movement. The capacitor consists of 2 semicircular metal plates. These plates are parallel and are separated by an air gap. To vary the capacitance, one of the plates is rotated through an angle theta using a spindle. The other plate remains fixed. So sketch a graph on figure 2 to show how the capacitance C varies with theta as the spindle is turned through 360 degrees. When theta is 0, the plates completely overlap. So pause the video now, unpause the video when you want to go through your answer. Right, in this question it's important to note that you will get your biggest capacitance when the plates are fully overlapping, because you'll then get the biggest potential difference between the two plates. So the positive and negative will form the strongest uniform field when they're completely overlapping. So you can see that when they're completely overlapping, that they're going to have the biggest value of C. Now when they're not in alignment, when they're not overlapping, so to 180 degrees, well, therefore you're going to get a capacitance of 0, and then it bounces back up as it moves to 360. Now it's important to note that it's going to be a linear decrease and a linear increase because you've got a constant rate of rotation, and you can think about how they will overlap, and that will constantly change how much overlaps. The next question says, in one situation the variable capacitor is too large for the available space. The same maximum capacitance is required using plates that have half the diameter of the original capacitor. Explain with numerical detail 2 ways in which this can be achieved. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you answer this particular question? So you've got to think how we can have the same maximum capacitance required when using half the diameter of the original capacitor. So you look at your equation for your parallel plate capacitor of C equals A over epsilon 0 epsilon r d squared. So you can see that you can either insert a dielectric between the plates, and it's important to note that you would increase it by a factor of 4. So as a result, you can then counteract the fact that you got half the diameter, because if you remember in the equation we don't have diameter but we've got area. So diameter links to area by a factor of a square. So when the diameter is halved, okay, what that's going to tell you is the area is going to go down by a factor of 4. So therefore we've got to put a dielectric of 4 in to counteract that difference. But the other issue you can do is you can change that value of d. So you can reduce the air gap to a quarter of the size, again because it's being divided by that. So as a result, what it'll do is you'll have a quarter of the area and a quarter of the diameter, so the separation, sorry. So as a result, the two will cancel through to get the same value. Now note it says explain with numerical detail, so with that we actually had to say how much the value would be changed. Let's now have a look at some questions regarding thermal physics. So the first question says, figure 1 shows an electrical steam iron. Water from a reservoir drips into the electrically heated metal plate. The water boils and steam escapes through the holes in the metal plate. The electrical power of the heater inside the iron is 2.1 kilowatts. Assume all the energy from the heat is transferred to the metal plate. The metal plate has a mass of 1.2 kilograms and is initially the temperature 20 degrees Celsius, and the heater is switched on. After a time t, the metal plate reaches its working temperature of 125 degrees Celsius. Calculate your value of t. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing you notice is in the question you're given the power. Now you should also remember that with specific heat capacity, that the equation where that incorporates in is that energy is equal to mc delta t. Now we also know that E is equal to pt, so what we can do is we can work out what the energy is, or in this case it says Q, by doing the power, which is 2.1 times 10 to the 3, because we don't work in kilowatts, we work in watts, multiplied by the time in seconds. Now again, if you read the question here, it says that it has been on there, so it's been on for time t, so we can say that it's going to be equal to 2.1 times 10 to the 3 times by t. We can then say, well, that substitutes into Q, and then equals the mass, which is 1.2, times by the change in temperature, which is 125 minus 120, times by the heat capacity. We then rearrange it and use that to work out t, which is 27 seconds. The next question says the metal plate is maintained at its working temperature. Water 20 degrees drips continuously onto the metal plate. Steam at 100 degrees Celsius emerges continuously from the iron. The maker claims that the iron can generate steam at a rate of 60 grams per meter. Determine whether this claim is true. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, what you've got to understand is that the power supplied in time t will raise the temperature of the mass of the water and convert it into steam. So what you should be doing is you should then be using an equation to work out different values. So what we can say is that the energy supplied, which is the power times by time, is equal to mc delta t plus ml. And as a result, we can use that to work out what P is, because in the question, we've got the heat capacity, we've got the specific latent heat, okay, and then what you can then do is we've got the mass as well, so as a result we can work out what the power is, and then as a result we can link that back into how we can generate steam at 60 grams per minute by working it out as such. So you can work that then through to work out your value. So you can work out your power to be 2.6 times 10 to the 3 watts. We can then work out how many grams that would then convert per minute, and then you can see if the value is correct. Now again, it's really important to note in these questions you actually answer the question asked, so you've got to evaluate and say whether the claim is false or whether the claim is true. So the idea is it is probably false because, okay, it's not going to be supported by the values, because the calculated quantity you're going to get is going to be not the same as the value that you need. The next question says, in the kinetic theory model, it's assumed that there are many identical particles moving at random. So state two other assumptions made in deriving the equations PV equals a third n mc RMS squared. Then explain why molecules of a gas exert a force on the walls of a container. Refer to Newton's laws of motion in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, you've just got to know the assumptions of the molecular kinetic theory. So they are: the volume of the molecules or the volume of the particles is negligible compared to the volume of the container or the volume of the gas. Okay, but remember, you can't just say the volume of the gas, you've got to say the volume of the container which the gas is in. And then you can also say that the collision time is negligible, or it's very small compared to the time between the collisions when the particles are in motion. The collisions between all the particles and the containers are elastic, which means that kinetic energy and momentum is conserved in these collisions, and that finally there are no attractive forces between the molecules or the particles when they exist in the gas state. Now, you can also got to be able to explain how a gas can exert a force on the walls of a container, which links back into paper 1 and the idea of mechanics. So it's the idea that when a particle collides with the side of a container, there will be a change in velocity, so therefore there'll be a change in momentum. Why is that? Because we're changing direction, and velocity is a change in speed or a change in direction. Or if you want to think about it mathematically, it goes from a positive momentum to a negative momentum, so therefore there's a change in the momentum of the molecules. So what we know from Newton's second law is that Newton's second law is the idea of that the resultant force is linked to the rate of change of momentum. So because there's a rate of change of momentum, there will be a force produced onto the wall. Now again, with Newton's third law, the force on the wall and then the force on the molecule must be equal yet act in opposite directions, because they are a third law pair. So you've got the same magnitude of force, the same type of force, but they act in opposite directions on different objects. So as a result, you'll get a force on the particle. The next question says, a sealed flask of volume 0.35 meters cubed contains an ideal gas at a pressure of 220 kilopascals. The mean kinetic energy of the gas molecules is 6.7 times 10 to the minus 27 joules. So calculate the amount of gas in the container. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this particular question? So, first question is, how can we link the different equations together? So we should hopefully know that the kinetic energy of one gas particle, we can look at our equation sheet and we see that it's 3 over 2 kT. So straight away we've got the mean kinetic energy of one particle. We know what K is, so we can use that to work out the temperature. So we pop that in and we make T the subject, and we get T out to be 324 Kelvin. Remember, in this equation the temperature is given in an absolute, so it's in Kelvin. So then what we can do is because the question's asked us to work out the amount of gas, is we've got to work out how many particles are present. So as a result, we can then use one of the equations to say, like, EK is equal to a half MC RMS squared, to then we can work out what N is going to be, or we use PV equals a third NMC RMS squared to work out our value of N. Or what we could also do is use now our equation of PV equals nRT to work out small n, the number of moles. So we could say number of moles is PV over RT. We've just worked out what T is. We know R, it's the molar gas constant. It's given in the equation sheet. We've got a value for pressure, 220 times 10 to the 3, because we don't work in kilopascals, and we've got a volume of 0.35. So that allows us to work out how many moles that we have, and then we can work out our answer to say the answer is going to be 29 moles. Now the next question says, figure 2 shows a variation of pressure with volume for a fixed mass of an ideal gas at a constant temperature of T. Draw on figure 2 the graph for the same gas at a temperature 2T. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So you've got to have an understanding of what the actual graph is showing, so the PV graph. So you would draw a graph with the same concave shape, because it's going to have the same trend, because it's still pressure and it's still going to be volume, which is a different temperature. But now it's going to pass at points, okay, where it's going to be higher. So you can see here it's passing through the coordinates of 2 and 8, 4 and 4 and 8 and 2, because you can see that with the increased temperature there, well, it's going to increase both the pressure and the volume of the gas. So you've got to think to yourself, how would it affect it? It would just call both of them to double. So whilst the PV value is going to be constant, then as a result, okay, it's just going to be increased values, because when you've increased your temperature, well, therefore you've got a higher pressure because the particles are moving faster, and also you're going to increase volume because the particles are moving further. So it's the same trend but just higher. Let's now have a look at the magnetic fields topic. So this question says figure 7 shows a transformer. Explain the functions of the core and of the secondary coil in the transformer. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's the core and what's the secondary coil? You've just got to know this. The core is what provides a great flux linkage or increases the flux linkage from the primary coil to the secondary coil. So it's directing, it is concentrating, it is funneling, it is focusing the linkage from the primary coil towards the secondary coil. Now, what is the point of the secondary coil? That is where we get a change in magnetic flux linkage passing through it, or there's a change in magnetic flux linkage, the field lines going through a conductor. So as a result, because there's a change in flux linkage going through the secondary coil, it tells us that we're producing an EMF or inducing an EMF. That's Faraday's law. So therefore, we can work out what the actual value of the EMF is going to be by looking at the ratio of the number of turns of the secondary and the number of turns of the primary. You can see that's a big deal in the question because they make a big deal about having a different number of coils on this particular transformer. Now the next question says figure 8 shows the cross section through a transformer core. The thin iron sheets are separated by arterial M. Explain how the efficiency of the transformer is increased by constructing the core in this way. And then figure 9 shows a schematic diagram of a power transmission system. Voltages between 33 kilovolts and 400 kilovolts are used for long distance transmission. Suggest why engineers have chosen 132 kilovolts for this system. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you should understand is when you see an M in this particular transformer, well, M is going to be a insulator. Now, when we cover a material in insulation, that is called lamination. So these laminations or laminates are made from an insulator or high resistivity material. Now, why do we have this? Well, this reduces the impact of eddy currents in the transformer because they've got such a high resistance, you won't get a high current forming. Now, because if you look at the question, it's 3 marks, we need to think about other features of this which will increase the efficiency of the transformer. Well, you've got to think of the idea that because we're using thin sheets or laminates of iron, we'll get smaller EMFs induced in the core, so we won't get that high enough eddy current. And also we'll note that the thin sheets of iron are used, the resistance is going to be higher, so as a result, once again, our eddy currents will be lower. Now, the other thing to note is it makes a big deal that we're using iron in the core. Now, the iron is important because the iron can magnetize and demagnetize very easily. It's a soft magnet, so therefore what you're going to have is you're going to have it's not going to have much energy loss due to hysteresis, so that's another reason. Now the next question, why would you use 132 kilovolts for this system? Well, you've got to look at the different values and compare, because if the voltage is lower than 33 kilovolts, then the power transmitted is at a high current. Think about why this is, because V and I are inversely proportional in a transformer. When V goes up, I goes down, and vice versa. Now we know the equation for power loss in a cable is P equals I squared R. So if we have an increased value of I, it will have an increased power loss in the cable. So as a result, we don't want it any lower because we'll have the current is too high. But then you've got to also think, why do we have a really high volts? Why not higher than 132 kilovolts? Well, it's because if the voltage is too high, this will create major difficulties with keeping the circuit insulated and isolated, because there'll be a massive potential difference with the surroundings, so therefore it could cause an electrical discharge. So you can't have that big of a potential difference. Remember, electrical shocks are caused by a large potential difference between the objects. The next question says the industrial consumers use 72 megawatts of power. Transformers 1 and 2 each have an efficiency of 98%, and the transmission line has an efficiency of 94%. Calculate the current in the 25 kilovolt line from the power station. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to remember that efficiency is going to be the useful power out divided by the total power in. Now, we can also use that the current is P over V to work out particular values. So what you've got to do is you've got to work out at each point in your national grid system what the power is going to be after you've considered the efficiency of that, and then what you do is at the end you work out the current by doing I equals P over V. From the P that that you've just got left and the V that you've got right at the end, because you know it's going to be 25 times 10 to the 3. So the first point is at 132 kilovolts. We know that it's got an efficiency of 98%. So we do 132 kilovolts times by equals 72 over 0.98. So therefore we're going to have 73.5 megawatts at that point. And then you can see that the next section, that's going to have an efficiency of 94%. So we multiply that by 0.94 and we get that's 94%. So therefore the transmission at the start is going to be 78.2 mega EV. And then what you can do is then work it all through, and then you can work out your values, pop them all in, work it out the end by doing I equals P over V to work out our answer to be 32,000 or 3,190. Let's now have a look at the nuclear physics topic. So the first question says, fission and fusion are two processes that can result in the transfer of the binding energy from the nuclei. State what is meant by the binding energy of a nucleus, then calculate in MeV the binding energy of a nucleus of iron 5626 Fe. So pause the video now, then unpause the video when you want to go through your answer. So the first question is all about definitions, and you've just got to learn it. That the binding energy is the work done required to separate the nucleus into its individual nucleons, its individual protons and neutrons. So it's how much energy is needed to separate out your nucleus completely. Now in the next question, how do you work out the binding energy? So what you've got to do is you look at the values here and you work out the mass defect. Now you work out the mass defect by working out the masses of the individual nucleons, and then we subtract the mass of the nucleus from that, because that's the difference. So we see that there are 26 protons in iron, so we do 26 times by the mass of the proton. That is given to you on the equation sheet. You can see here that 56 minus 26 is 30, so we've got 30 neutrons. So we know that we do 30 times by the mass of the neutrons in kilograms, which is given on the equation sheet. You add them together to get the total mass of the individual nucleons. You then subtract that from the mass of the nucleus, and then as a result you then got your mass in kilograms. You can then convert that into joules by doing our equation E equals mc squared. Now that gives us our value in joules, so E equals the mass deficit times by the speed of light squared. We can then convert that into MeV, because the conversion between joules to MeV is times by 1.6 times 10 to the minus 13 joules. So we get our answer out there to be 490 approximately. Now the next question says, figure 10 shows how a graph of average binding energy per nucleon against nucleon number for common nuclides. So the nuclide labeled X in figure 10 undergoes fission. Annotate figure 10 to show one possible pair of nuclides resulting from the fission of X. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So you've got to think that F1 and F2 have to be to the right of the peak, and they're marked on there in the x-axis. Now again, they've got to be in the correct region, so they're symmetrical to about half the nucleon number. So what you've got to understand is that the two values have to approximately add up to equal that value of about 240. Now again, you've got to remember that it won't exactly add up to what the value was for the original nucleus, because you'll lose a couple of nucleons to become free neutrons to then carry on the fission process. So you'll see here they've got to be roughly symmetrical, two smaller values, they add up together to then give a couple of values smaller than the actual nucleus that you started with. The next question says, figure 11 shows a graph of N against Z for stable nuclides. Deduce the likely mode of decay of F1 and F2 and refer to figure 11 in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you look at what the values are for the fission fragments given in your first question. Now you'll notice that in this NZ graph that all the fission fragments will want to move towards the stability belt. Now the issue with both the fragments that you'll produce is they'll have a high ratio of neutrons compared to protons, N to Z. So that tells us that we've got too many neutrons compared to protons. So therefore we want to get down to the stability curve, we want to move closer to the stability belt. So as a result, we've got too many neutrons, so we're going to turn a neutron into a proton. So therefore, it's going to have to be the beta minus decay, because that in that process, you're turning a neutron into a proton. So as a result, it will move closer towards that stability belt. So that brings an end to our revision session in today's lesson. So if we've been successful and we've learned in today's lesson, we'll be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for AQA A-level physics. So thank you very much for watching this particular revision session for paper 2 in AQA A-level physics. Thank you very much for watching and have a lovely day.